Hey, let's talk about section 5.2, inverse functions. Okay, so let's start by just talking about things we already know. So inverses. If we say additive inverse, so the number 4 has a number that I can add to it to get to 0, right? And we know what that number is. Isn't it negative 4? Right? Negative 4 plus 4, that's 0. So if I've got just any number a, the number that I add to it to get to 0 is negative a. So what we would say is that the additive inverse of a is negative a. So great, we know what the word inverse means, right? So something that we're going to say in general about inverses is that an inverse for an operation is the number or object that we use the operation with some other number to get to the identity. So 0 is the additive identity, right? So the number that I add to any number at all to get to the additive identity is negative a, right? Okay, we can see, let's have a different example. So instead of additive inverse, we can think of multiplicative inverse. Multiplicative inverse. So I have some number and I want to multiply it by some other number to get to the multiplicative identity. So multiplicative identities. This is the number that I can multiply by any other number and get the same number back. So we know that that's 1, right? I can multiply any number by 1 and I get the same number back. So multiplicative inverse, this is the number that I multiply by any old number at all to get to that identity. So we know that this is 1 over a, right? The thing that makes this different than the additive inverse is that every real number has an additive inverse. It's just the negative of that number. Where multiplicative inverses, not every number has a multiplicative inverse. In particular, the number 0 does not have a multiplicative inverse. So, right, if I do 1 over 0, that's undefined, and that's not a real number. So, not all numbers are going to have inverses. Okay, so bringing this back to what we're going to be talking about here in a second, we're going to find inverses for a different operation. Our operation is going to be composition. So we just talked about composition in the previous section. So what we're going to end up doing is having something like f composed with some number or some value is the identity. So we have that x is the identity for functions, right? Because if I have my function f of x equal x, whatever I put in for my input, that's going to be the same as my output. So that's an identity function. So we want the function that we put in this position here. So I compose f with that function. We want to get back to the identity. Well, we're going to start out by just saying, hey, if this happens, if there is a function such that this is true and that it works out the other way as well, then these things have to be inverses. So we're kind of taking a little bit of a backwards approach here. So we say that if these two functions have these two properties, right, if I compose them in both directions and I get the identity function out for both, that means that these functions are inverses of each other, and we say that f and g are said to be invertible. Okay, so going and checking if functions are inverses is pretty straightforward. We're just going to find the composition. So f composed with g of x. This is f of g, right? So we're going to put the function g inside the function f wherever we see x in the function f. So we got 6 times this stuff. Minus 2, right? This is the function f where g is in that x position. And then we can multiply everything through. So we got 6 times 1/6 is 1. 6 times 1/3, that's 2, minus 2. Okay, so that is x, and it worked out. Super. And then we can do the other direction. So composing these in the other direction, we got g of f. So we got g of 6x minus 2. So now we're going to put 6x minus 2 wherever we see x in the function g. And then we can simplify. So we multiply everything through. We got x minus 1/3 plus 1/3, and it is x, and that's great. So we confirmed it. And we say, yes, these functions are inverses, because we compose them both ways, and we get the identity back. We can do the same thing with rational functions too. We can do this with any type of function, right? So f of g, we can do this, right? Put the function g in for x wherever we see it in the function f. So we got 3 over 4 minus 4x minus 3 over 4, not 4x. Okay, and now we do what we usually do with complex fractions. We want to simplify this thing so we can multiply by x over x, provided that x isn't 0, I suppose. And we can do that, right? In the numerator, we're just going to have 3x. The denominator, we multiply by both of these terms here. So we got 4x in the denominator. And then multiplying by this second term here, that denominator is just going to go away. So we got 4x minus 3. Okay, simplifying this down now, we got 3x over 4x. Now, distributing that negative, we got minus 4x plus 3, so that's 3x over 3, which is x. So that checked out. And now what's the only thing left to do here is to check the other direction. So we want g of f of x. So g of 3 over 4 minus x. And we're going to put now 3 over 4 minus x wherever we see x in the function g. All right. Great. And then we can do the same thing here, right? We're going to multiply both the numerator and the denominator by 4 minus x. And that's going to make all of these complex fractions go away. So we can do that. Multiplying through there. In the numerator, we just have 4 minus 3 times 4 minus x over, then that's 3. All right. I forgot about that 3 there, right? We would have 4 times 3 here, and that would be 12. So, oops. Okay, and then we just want to keep on simplifying. We've got 12 minus 3x. No, minus and negative would be a plus, right? So we've got plus 3x over 3. So that's 3x over 3 equals x, and we're good. So we say yes. These things are inverses of each other. That's great, and we can verify that. So this is going to be the step that we're going to be doing at the end of our process eventually, where we want to check to see if we did it right. Okay, good. So now we're going to have a whole bunch of properties of inverse functions. So let's maybe think about what it is that we're saying here. So we're saying if I apply the function g to the function f, it's going to get us right back to the input from f. So g is the function that's going to take my output from f, and it's going to put me right back to the input where f started. So we can draw a little diagram here. If this is A and B, so this is the domain set A and the range set B for our function f. My f is going to take that number over to f of x. And then the g, like when we're composing f with g, and we get right back to f, that function g is taking this number here and bringing it right back to x. So essentially these functions are just undoing each other, right? And that's kind of what we should think about and maybe put the pieces together, like when we were thinking about additive inverses, right? So these were numbers that undid the action. So think about maybe if I'm solving an equation, if I've got 2x equal 5, I would want to do the inverse operation on both sides to make that go away, right? 1/2 would be the inverse, 1/2, right? Multiply both sides by 1/2, and then we're left with the identity. Well, the identity in this position is 1, right? So, okay, so inverses undo the operation. So we've got these properties, right? So the domains and ranges of inverses are just flip-flopped, right? The domain of f is the range of f is the domain of G, and the domain of f is the range of G. And that was, I guess, if I had my little picture up here, right? G is taking things from the range of f back to the domain of f. So the domain is the range, and the range is the domain, and vice versa, okay? Super, super, super. All right, so another way to say that is if I have a function value from f, and I got there with the number a, if I would apply g to the value b, I'm going to get right back to where what the input was from f. All right, so the next one, AB is on the graph of f if and only if, well, that meant that AB was on the graph of f. So on this one, the point BA is on the graph of G. Okay, so what we're going to maybe real fast, we can relate these things here, right? So the second part of this little theorem here says that the graphs of inverse functions are reflections of each other about the line y equals x. So let's think about this for a minute. If I've got a point on a function, 3, 1, doesn't really matter where it is, the point on the inverse would just be flip-flopping those coordinates. So if we flip-flop those coordinates, we would be at 1, 3, and those points are reflections of each other about that line, right? All right. Okay, good. So I guess in the statement of this theorem, we've got a little bit of new notation here. Something else to be careful with, a little superscript -1. We are used to that being an exponent, but in this context, this means inverse. So I guess be careful with that, just in context. In our function notation, that means inverse. Okay, now we're getting to the good stuff. A function f is said to be 1-to-1 if it matches different inputs to different outputs. So that means if I've got two different inputs, they must have two different outputs. So for any two numbers in the domain, they cannot have the same function value unless they are the same number, right? So yeah, let's think about this graphically here. So consider this function here. So we know that the square function, we know that looks like a parabola, right? And we can use our imagination, pretend it hits that x-axis. So we want to decide if this is 1-to-1. Well, in particular, I know that the point 1, 1 is on here, right? I just don't like it when that does that dragon thing. So 1, 1 is on this function. We also know that the point -1, 1 is on this function, right? So what we have here is two outputs, 1, are the same, but their inputs are not. Right? So what we've just exhibited here is that this function is not 1-to-1. One-to-one. Okay, so if we think about the other one here, 2x plus 1, we know what that looks like. It's got y-intercept 1, and it's a line with slope 2. How beautiful. And then we want to say, is this 1-to-1? Well, think about whether or not any two function values are ever going to be the same along this line. Well, it never turns around, so it's always increasing, right? And if it's always increasing, we're never going to have two function values that are the same, right? So this one is 1-to-1. And maybe we can justify ourselves by saying that it's always increasing. Right? On the whole domain, it's always increasing, so that means that we're never going to repeat a function value. Okay, so what we can put this kind of together to mean is that, well, if I can draw a line, a horizontal line that intersects my function more than one time, it can't be one-to-one. So on this one down here, if I draw any horizontal line ever, it's only ever going to intersect at one time, and that's it, exactly once. Well, that's what we're going to call a horizontal line test. So a function is one-to-one if and only if no horizontal line intersects the line, or excuse me, intersects the graph more than once. So if it does, then we say that it's not one-to-one. Well, what's going to happen with one-to-oneness is that this is going to tell us that a graph, or excuse me, a function is invertible. It means it has an inverse. Let's think about an easier little example with numbers. So 1, 2, 3, 4, 5. Maybe this goes to 4, this goes to 5, 3 goes to 4. All right, so if I call this my function f, f takes the domain A over to range B. Now, what's going to happen if we do it backwards? So if we go backwards, and I would say, okay, well, if I'm at the value 4, which domain value got you there? Well, 4 is paired with both 1 and 3. So if I would flip this around and make my function go the other direction, so if I wanted to go the other direction, that would not be a function at all, because now two numbers are associated with this domain value. So this kind of hand-wavy way of saying, or showing, I guess, why we need functions to be one-to-one to have inverses. Because if they're not one-to-one, then doing it backwards is not going to be well defined. It's going to have two or more values that we're going to point to. So yeah, all these things mean the same thing. F is invertible, F is one-to-one. The graph of F passes the horizontal line test. Okay, so now we're going to get to actually finding inverses. So finding inverses of one-to-one functions, we're going to first rewrite our notation. So we're going to say f of x is y, and then we're going to interchange x and y, right, because the domain and range switch places. Right, that's the whole thing with inverses. Our domain and range are just flipping around, and then we're just going to solve for y to get our inverse, because we usually want to write a function in terms of x, so we're going to do that. So let's go for it here with 42 minus x. So we'll just do the steps, right? One, we're going to rewrite y instead of f of x. Cool. Second step, we're going to switch x and y around, so they just trade places. That's good. And then the third step, this is going to be the hard step. We're going to solve for y. In this case, this one's not so crazy, right? And then we would say f inverse is 42 minus x. And then we're done. Now, we should check this. So to verify, check that if I compose f with its inverse, we get x, and if I compose the inverse with the original function, we also get x. So we should go and check this and verify that it's true, but I'll leave that to you to verify this, because it's absolutely a good idea to check yourself and make sure you did these things right. Okay, good. Okay, part B, we want to do the same thing. We want to find the inverse of this thing. I guess we sort of glossed over the fact that this thing is one-to-one, didn't we? We didn't even really ask that question, because we know that any linear function, this one in particular is going to have y-intercept 42. It's going to have -1 for a slope. It's going to look kind of like this. There aren't any horizontal lines that we can draw here that are going to intersect it more than once, so we conclude that it's one-to-one. It is true that every linear function is one-to-one except constant functions. So constant functions are those that are horizontal lines. So those are not one-to-one, but any line that has a non-zero slope is going to be one-to-one. Okay, So we can do the next one. We've got 2 minus square root x minus 5. And we have to decide if that's 1 to 1, right? We should probably decide that real quick. Well, we know what the square root function looks like. Looks like this. And that's 1 to 1. Well, what about a transformation of it? What would that even look like? Remember this from the transformation sections, right? We're going to move right. We're going to move right 5 units. We're going to flip it about the x-axis, then we're going to move it up 2 units. So what it will end up looking like is this. And that is 1 to 1, right? Because we can draw a horizontal line on there anywhere, and it's intersecting at only one time. Okay, so let's find the inverse. First thing we do is we rewrite y instead of f of x, and then we interchange x and y. So we got x here, and we're going to put y in place of x. Alrighty, and now we want to solve for y. So yeah, again, this is going to be the difficult step because we're going to have to remember stuff from our past, right? How do I solve a radical equation? Well, first we want to isolate the radical. So we get that 2 on the other side. And then we want to divide everything by -1, right? To get that. Well, you know, we don't need to do that. Why don't we just square both sides at this point? Because that negative is going to go away if we square it, right? So if I square both sides now, that negative is going to go away. On the left, why don't we just leave this as x minus 2 squared because it looks prettier. And then if we square this guy, squaring a negative makes it positive, and then squaring a radical just gives us what's under the radical. Okay, so then we can come over here, and we've got y is equal to x minus 2 squared plus 5. Okay, now we want to rewrite that with our function notation. And now now we've found it, right? And we can go ahead and verify it by composing the function with the proposed inverse and vice versa, and making sure that we get x. So something else we ought to think about is what we talked about before with this functions are reflections of each other about this line. Think about what this shape is. It's a quadratic, isn't it? So we got squared on the x, so that means this is going to look like a parabola. Well, what's the vertex of this parabola? The vertex here would be 2, 5, wouldn't it? So that's going to be like somewhere in here. And it's a parabola, so it would look like this, but it's not the whole thing, right? Well, think about our domain restriction, or excuse me, think about what the range was for this function right here. Sorry about that. Okay, sorry, I had to take a little break in the video there. I kind of forgot where we were at, though. So we had just drawn a picture of that parabola, and we were saying, hey, that's not a reflection. We need to take off one of those branches, right? We wanted this one. And maybe we can say something about the domain. The domain of f in this case is this. So f is the radical function. The domain of this thing is what? It's everything bigger than 5, right? X has to be bigger than or equal to 5. So that was 5 to infinity. Well, the domain of f, this is going to be the range of f inverse, right? Okay, well, that matches, right? The domain of f inverse, at least that matches with the picture, right? It's a parabola that has vertex 2, 5. So it's going to start at 2, 5 and go up, right? So our range agrees. Now we want to say something about the range of f. That's the same as the domain of f inverse. So the range of f, based on our little picture of our transformation, this is everything that is less than 2 or equal to 2, right? From our transformation picture, what we knew about this function here, it had to be 2 or less. Well, that's going to be the same as our domain of our inverse, because we might point out that, hey, that's a parabola. The inverse is a parabola, and parabolas are not 1 to 1. But it is one-to-one if we restrict the domain here. All right, good. So yeah, something we ought to do is compare domains and ranges of each of these, because we're going to be asked, find the domain, find the range of these things. Okay, and now here we've got another one here with a parabola, right? So this figure here is a parabola, and they're specifying here that x is greater or equal to 5. Now let's do a little bit of thinking here before we start. Let's rearrange this thing. So f of x, this is in general form. Let's put it in standard form. So we want to complete the square. We remember what we do here. We're going to add a number and then subtract that same number, right? We did this back in the section with parabolas. So we're going to add half of the coefficient on x and square it, and we're going to subtract half the coefficient on x and square it. All right, and now we've got a completed square. So we've got this part is x minus 5, quantity squared, and then we've got minus, what is that? 5 squared is 25. So if we were going to draw a picture of this, this would be a parabola with vertex 5, negative 25, and it opens up, right? So if we drew a picture, it would be a parabola at 5, negative 25, and it opens up. Well, that function is not one-to-one, so we cannot do this. That's why we're saying make x be bigger than or equal to 5, because then we're just taking the right-hand branch of this. Right, so something that we can take away from this visualization is the range of this, right? So this is the domain of f. We know that the range of f can be found using the vertex, right? So it's negative 25 and everything larger than that. All right, let me rewrite that. Negative 25 to infinity. All right, so this is going to be the domain of f inverse, and this is going to be the range of f inverse. And we can use this to maybe verify what we've done after we do it. Okay, so good. We want to find our inverse. We've got our function, so we'll just do the steps, right? Say f of x is y. We're going to switch the roles of x and y, right? The domain becomes the range becomes the domain. And now we want to solve for y. So I got x plus 25 equals y minus 5 square. And then we do what we usually do with functions like this, or equations like this. We do a square root of both sides. Can't forget about the plus and minus part. So we have here, we'll flip that around too. Y minus 5 is plus or minus square root x plus 25, and then add the 5 to both sides. All right, so we have our inverse. F inverse is 5 plus or minus square root x plus 25. But that is a problem, right? Because this thing's not a function at all. It's not well defined, right? If I put in, say, x equal 1, for example, you're going to get 2 function values out of the deal. So that's a no-no. We can't have that with a function. So let's do a little bit of thinking here. Well, the range of f is the domain of f inverse. And is that true? So the domain of f inverse, we need everything under that radical to be either 0 or bigger than 0. So it's got to be bigger than negative 25, right? So yeah, that checked out. How about the domain of f has to be the range of f inverse? So the domain of f is x bigger than or equal to 5. So which one is that going to give us? Is the plus going to give us these values that are bigger than 5, or is the minus? So if I subtract something from 5, those things are going to be less than 5. So I need the positive one. So the domain of f is the range of f inverse, and that's 5 to infinity. So take the positive one. And we would say f inverse is 5 plus square root x plus 25. And we're done. Now, again, we can go ahead and compose these functions with each other to verify that we did the right thing, and I would absolutely encourage you to do that. But let's not leave that to you. Okay, so let's do another one of these. We've got another function here, and it seems like there was an awful lot of complication in this surrounding that step 3, right? That was 1, that's 2, that's 3. Step 3 is always going to be the hard part, and what you're going to show yourself in step 3 will sometimes cover up some errors we made initially. Like if we have to first go and decide, hey, is this function 1-to-1? Maybe we're not going to immediately know, and we're just going to have to try to find the inverse. Now, something like this is going to happen if it's not 1-to-1. We're going to get more than one thing as a possibility. So, be careful for these indicators that there's more than one value, which would indicate that it's not 1-to-1. All right. Anyway, let's do the same steps here. So our first step we're going to change that f of x into a y. Okay, and now we're going to interchange x and y, so the domain becomes the range becomes the domain, and now we want to solve for y. So we do the same thing all the time when we're solving rational equations, right? The first thing we do is we get rid of the denominator. So we can multiply everything by 2y minus 1. It's just going to cancel on the right side. On the on the left, let's multiply that through. Okay, so we're solving for y, so we want to get all the y terms on one side. So let's subtract that y from both sides, and let's add x to both sides. Okay, remember we're still solving for y, so we want to get y alone. We see that it's a common factor. And now we are almost home free here. We've got y equal, now we divide both sides by 2x minus 1. Okay, good. So at that point we would say f inverse is x minus 2 over 2x minus 1. So something that is of note here is that our original function happened to be its own inverse, which seems a little strange. But it's entirely possible, right? Something to watch out for. We might be a little weirded out by that, but it is entirely possible. And maybe let's just verify that we did the right thing. So let's compose the function with its inverse, or with its proposed inverse. So f of x minus 2 over 2x minus 1. Okay, so we've got x minus 2 over 2x minus 1 minus 2 over 2 times, whoops. Okay, so when we're simplifying this, we want to multiply both the numerator and the denominator by 2x minus 1. And we can do that, right? We're going to multiply through that first term. It's just going to cancel, and we're left with x minus 2. And the second one, we're going to multiply by 2. Negative 2 times 2x minus 1. And then the denominator, we're going to do the same thing. Those guys cancel. We're just left with 2 times x minus 2. And then this one, we got minus 2x minus 1. Okay, and now we're still playing the simplification game. In that numerator, we got x minus 2 minus 4x plus 2. The denominator, we've got 2x minus 4 minus 2x plus 1. Okay, now I've got, what do we have? What do we got? So x minus 4x minus 3x over, right, 2 minus 2 plus 2, those cancel. Then I've got these guys cancel out, minus 4 plus 1, that'd be 3 negative. So it worked out to be x. Okay, good. So at least that's half of verifying it. And we should go and also verify this, and I'll leave that to you to actually go and verify that. We need to show that it's equal to x, right, if these things are inverses. So anyway, we know what inverses are now, and that's so wonderful, and we can find inverses. So yeah, great. That was it for section 5.2. Thanks for watching the video, and have a great rest of your day.